This conference will now be recorded.
Okay, so good morning everyone and welcome back to a fresh new session on predictive modeling. Today is day 42 and we are talking about the statistical methods. We are talking about the, so we are kind of talking about the, the descriptive measures of statistics and with respect to the application in SAS, right? We are talking about it in that aspect. So in yesterday's discussion, we mainly what we did was we had discussed about the key descriptive measures. Right? So we started off talking about the descriptive measures of predictive modeling, and we started off talking about the measures of central tendency, the measures of dispersion, and the measures of asymmetry. So while we talk about the measures of dispersion and about the measures of asymmetry, and while we list out that, so in yesterday's discussion, we did two important things. First, we we spent some time in structuring the code such that we have appropriate macro variables there and appropriate configurations such that the code will just work appropriately. So and you will not be in a position to make those changes. Right? So you will not be in a position to just to hard code the data set names and all the variable names. So we just created appropriate configuration so that by changing the configuration part, we can generate the results for different variables at different points of time. So that's one of the part that we had done. Right. Now, our final objective, or our also one of the most critical objectives that we would have over here is to form an understanding of the portfolio. So, to do a portfolio, a full-fledged portfolio description for a personal loan product for the point of sales financing portfolio, which we would use for application model development, and to do the portfolio description for the credit card data or for the lending club data, so that and to do a portfolio description and perform a full-fledged data quality check exercise for these, right? So that we have an understanding of how exactly this can be. So how exactly is it that this data quality check can be done, and how is it that we can use those data quality checks to frame insights about the behavior of the variable. So that's the part that we need to understand for descriptive model methods, right? I need to understand how exactly is it that what interpretations can I make about a mean, median, and a mode. What descriptions can I create about about a variable by looking into its trend of mean, into its trend of variance, and into its trend of like into its trend of data and so on. So how do we do that? So what are the how do we use these descriptive measures to create best practice analyses of variables? To how do we assess the empirical distribution function? So how do we do that? So that is the part that we wanted to discuss. So discuss under this predictive modeling methods in SAS descriptive analysis methods. So before we go into that, we just take up one single variable and we use a proc mean, we use a proc univariate, and we try to enter deep into the variable and try to see its interpretation so that we can generalize it for the whole portfolio. How is it? So one of the biggest question is that how, by doing a portfolio analysis of two variables, of two continuous variables, can I distinguish between those risky borrowers and less risky borrowers? How do I look into the variable trends? How do I assess the trends? So how can I form an insight about the variable from a specific descriptive analysis measure? So these are the things that we will be talking about in this particular exercise, right? And we started creating that framework. We saw what are the key descriptive measures like, and from there we'll take up our discussion in today's session, right? So we will first we run the libraries, and we will create the rehash the configuration files. Right now, after this is done, the next part that we'll talk about is we'll take up one of the variables or one of the data set, and from there we'll try to see how to interpret about the behavior. So over here, while we talk about the behavior, the behavioral stuff, we can see that I have reported the number, the number of observations. We reported the sum, the mean, median. These are the basic descriptive measures of central tendency, absolute measures of central tendency. Then we have the relative measures of central tendency, where we published the percentiles, the 25th percentile, 50th percentile, 75th percentile, like this, 99th, and finally the maximum, the 100th percentile value, right? And then we reported the measures of dispersion over here, then on the standard deviation, range, and coefficient of variation. So we have reported both the measures of central tendency and the measures of dispersion for the variable, amount across the good and the bad flag. So in the German bank data, we have the target variable called the response variable. The response variable is defined as y equals to 1 if the borrower is good, equal to 0 otherwise, and therefore we'll report it across this 1 and the 0. So we'll see how is it that the amount variable is distributed across the 0, and how is it that the amount variable is distributed across the 1s. So the amount over here is the amount applied. So what is the amount of the credit for which the borrower had applied? And now the borrower, it is generally seen that borrowers who are applicants who come up with a greater exposure tend to, or the exposures of the defaulters tend to be relatively higher than compared to the exposures of the non-defaulters or the good borrowers. So we need to check how exactly is this amount distributions, how is the amount distributed across the goods and the bads, because the size of the goods is very different from the size of the bads. So that is something that we have. So let us, so what we do is we try to explain this part, right? So we'll form a basic description of this amount variable. Now, as we form a basic description of this amount variable, from there the next set of descriptions that we will also look forward to is we'll see how we can delve deeper into the behavior of this amount variable using these relative measures of central tendency. So, and then we'll talk about the univariate as well. Then we'll see how univariate results will help me dig deeper into the explanation of the variable. So we'll see at what levels are the expected or the observed, the empirical distribution of the behavior variable can be assessed. So if you're looking at a variable, what are the different ways at which you are going to assess this? So we have talked a little bit about this in the time when we are doing proc means and proc univariate in SAS. We'll delve deeper into this with this analysis. So over here, our focus is not much on the options of proc means and proc univariate. It is more focused on the statistical side of the description, right? So let us start. So let me just run this code first. So I'm doing the proc means for ref location 1. So the ref location 1 is the temp underscore p. P stands for predictive modeling, right? For temp p. And the reference data over here is the German bank based data. So the German bank based data in the temp p library is my reference data set. The continuous variable a over here is amount, and the target variable a is the response variable. So the continuous variable a is the and the target variable underscore a is the target variable. Then run. So let me run this part. Okay, also before I run this, one of the important discussion that we have had in the discussion in the last discussion is that we discussed the discourse of choosing mean versus median and median versus mean. So we looked into that part as well. Okay, so this is how my distribution looks like. So basically over here, what we had done is we have reported or we have identified a very basic distribution of the value, so of the amount variable, right? And and what we need to understand is that what is it that we get to see from this distribution? What is it that we get to see uh, from what are the inferences that we can draw about the amount variable from this distribution? What are the unanswered questions? So let me just start off with this common table over here. So I have obtained this result over here. The maximum is there, the standard deviation is there, the range is there, and the coefficient of variation is there. So basically, let me just introduce another concept. So over here, from this up to this point is your absolute measures of central tendency. Central tendency. Okay. Then what I have over here is the relative measure of central tendency. Over here, what I have is the relative measures of central tendency. And over here, I have the absolute and relative measure of central tendency. So absolute measure of dispersion. And over here, I have the relative measure of central, relative measures of dispersion. So there is coefficient of range as well, right, in this, but we'll just talk about the relative measure. We'll just talk about coefficient of variation because this is one of the most basic measures that we generally do, right? And this is obviously your target value. The target variable is the response variable or the bad flag variable. This is the target variable, right? So over here, so you have 90th percentile, 95th percentile, you have the 50th percentile, 25th percentile, and so on. Now, the next part that we have, so this is the level one descriptive analysis, or let me call this the overall descriptive analysis of this failure. Now, the question is that how do I, or what information will this give me actually? So let's have a quick look into this. The first thing is the mean of the 0 versus 1. So 0 is, the 0 over here is the bad customer, and 1 over here is the good customer. Good customer. No, the good and the bad customer. Now, one of the question that I have is that, so let's try to see the differences in the approach that we have. So how is the distribution different between, for the amount variable, between the good and the bad customer, right? So is it that the bad borrowers have a greater exposure compared to that of the good customers? So that is something that we need to test. Then we need to see that how many of, so does this distribution have an outlier? Now, if there is an outlier, how do we treat those variables? Or do we treat them as, say, as a separate segment? How do we treat them actually, right? So that's the part that we need to talk about. So first of all, let's try to see how the distribution, or what inferences can we draw about the distribution of this variable, about this amount variable. How is it that I can draw that? So first of all, let's look into the number of the bad and the good customers. So the percentage of customers, the percentage of customers, is the difference is like this, that out of the 1,000 acquisitions which has happened, out of them 300 customers are bad customers, and 700 customers are good customers. So nearly the percentage of the bad borrowers is 30%, or out of the 1,000 acquisition which was done, 30% of the accounts has turned out to be bad, right? So that's something that you can clearly see from here. Now comes the next part. The next part is the total sum of the exposure. So what proportion of the total exposure has been given out to the good customers, and what proportion of it has been given out to the bad customers? So that is something that we need to see, right? So let's say the percentage difference, right? Right. So I have this. So the number of observations, the total number of observation over here will be 300 divided by the sum of. So just let me fix this sum over here. That's 30% and this is 70%. So it's a perfect 70-30. Now over here I'm looking into the, so this is the volume, or let's call it the distribution of the population or the base, or let me call this the volume, the total volume of the customers. Now this is the total exposure, or the total amount or the total balance that we have over here. So the exposure over here is this divided by the sum of this plus this. So it shows that 36% of the exposure is there with the bad borrowers, and nearly 63% of the exposure is there for the good borrowers. 63-64%. So basically one thing we can see is 30% of the exposure, 30% of the accounts having 36% of the exposure, and 64 and 70% of the base having the remaining 64% of the exposure. So it clearly shows that. So this will kind of give me an idea that the average balance that we have over here, the average, will always be higher for the bad borrowers. So the bad borrowers is always expected to have a higher concentration or the higher average amount of the average, a higher average amount applied, right? So the borrowers who had applied, so who turned out bad, so out of the bad base, if you see the average amount which was granted to them, and so on. So then what you would see is that, or the amount that they had applied, so you will see that on an average, the bad borrowers tend to apply a higher amount. Now the question is that this is an average figure. Now the average figures are not always very reliable figures, right? So they are not always very reliable figures. So therefore, it is always important to also look into the median figures, because averages, as we discussed yesterday, has the tendency to get impacted by the tail end figures. But if you are looking towards a, so if you are looking towards a uh, what should I say? So if you are looking towards like if you're looking towards a mean, then with the outliers you can get actually so you can get a distribution which is affected, or the mean will be affected by the extreme values or the extreme outlying values. Now on the other hand, another important thing is that with median, if you compare the median is free from such external fluctuations. Therefore it is always important that you look into, so whatever like you are seeing, and whatever the average figure that you are comparing, you need to compare both the mean and the median figures, right? And to form a general conclusion. So over here, if I'm talking about the mean and the median, so one of the things that I see is that the mean and the median for the bad customers are higher compared to both the mean and median of the good customer. So one thing that we can clearly say is that on an average, the amount of credit that a bad customer would always try to apply, right, for would always be on the would always be relatively higher than that applied by the good customers, because the bad borrowers are borrowers who, so one way is that they, so the bad borrowers, either they are unable to, because borrowers who tend to go default, right? They are unable, they are using a credit because they are unable to manage their finances. And given that they are unable to manage their finances, what they are doing is they want to take a product, right? So they're applying for this credit. So obviously, and obviously their expenses, their the credit that they take would also be on the higher side, because anyways, so so most of these, so some of these borrowers are with full defaulters, they know that they would not be able to take it up, so they just take a high amount of credit and they go into default. Also, accounts which take higher volume of credit are less likely to repay them back, or would have a lower probability of would have a higher probability of defaulting, because simply everything else remaining unchanged, they are surely exposed to a greater volume or to a greater exposure compared to the other borrowers. So therefore, because someone who is taking a higher exposure loan or applying for a higher exposure will always have a higher amount to repay, and hence are the higher chances of defaulting. So that is something that we need to take into account, right? So these are the two most important observations that we would have. Now what we need to do is we need to compare the, so we now need to compare the distributions between the good customer and the bad customer across different percentiles, across different across the mean, across the median, across some important percentiles. And what we also need to do is we need to see that how is their range, how is their coefficient of variation, and all these things, so which are more stable and all. So that's something that we would want to see as well, right? So over here, what we need to do is we need to assess the percentage deterioration or the percentage difference. So over here I'll create another table which I call the, over here I will map the percentage difference. I have mean, median, minimum. So this is the percentage difference that I am looking at is for the central tendency measures. So similarly, I look at the central tendency measures, and similarly I look at the percentage difference for uh, the measures of dispersion. This is measures of central tendency. Okay, I think Shiva has a question. I'll just take that question up. Okay, so Shiva has a question that if mode is missing, we can make above observation. Right? Yes, we can always make that above observation. So that is dependent not only on mode but on a whole set of other factors, right? So, but yes, and as far as you are talking about the right-skewed distribution, the mean is always greater than the median, and obviously the mode is generally greater than the median is greater than the mode if it's a right-skewed distribution. But yes, if you have to plot the distribution, then you'll obviously need the mode for making the conclusion whether the distribution is a right-skewed distribution or not. right? So because I have not yet done the mode will be generated as a result of your univariate measure. So let's come to that first. But before that, let's try to assess the important so assess the variables difference between the good and the bad for this shared distribution, the one that we have. Then once we do the univariate analysis, we can focus on the mode and on the shape of the distribution and the plot of the distribution. So using median, so using the proc means, the result that we have generated is just there to give us an insight into the average behavior, into the overall average behavior of the variable, right? So let's just try to see how is it that this variable is behaving across the good and the bad customer. Now this will also give me an idea as to whether I can use this amount variable as a strong variable for model development. So if I incorporate this variable into the model, will this help me discriminate between the good and the bad? So that is what I'm trying to assess through its distribution. So, and if I look into the overall distribution, instead of just looking at the average distribution, I can make a better conclusion, right? The conclusion that we make by looking into the entire percentile distribution and all, as well as the relative measure, the absolute and the relative measures of dispersion, is more robust than than the conclusion that you make just by looking into the average, the differences in the average. Right. So let's try to see the difference in the mean. So the difference in the mean will be the mean of the bad customers from the mean of the good customers divided by so the mean of the two groups of customers is different by 13.1991%, nearly 32. So there is a so the mean of the bad borrowers is significantly more different from is 31% more than mean balance of the good customer. So one thing that you can see is that the mean balance of the bad borrowers is much higher than the mean balance of the good borrowers, right? And there is not a very close difference of 4, 5, or 10, or 5, 8, 7, 8% or 10%, but it is like nearly 32%. So there is a 32% difference between the mean balance applied by the mean amount applied by the bad customers versus that of the good customers. So it clearly shows that the bad borrower customers who go bad generally have a higher credit appetite. There, because their exposure is relatively larger, so there are always higher chances of them being defaults. Okay. So the next part that we have is the difference in the median. Now I can see that there is a difference in the mean. Now I believe that these two distributions are skewed distribution, therefore that can reflect as a the skewness can be a result of that deflection in the mean. So I have a mean 13.91%, right? 31.91%. So let's see how would this difference translate into the difference in the median. Now the median itself is not kind of affected by the outliers. So one thing that you can see is that the difference in the median is 14.73% for the bad customer versus that of the good customer. So we can see that the median amount applied by the bad customers is also higher compared to that of the good customers. So I have that difference of the heterogeneity in the behavior is clearly reflected as a difference of the mean and the median figures, right? So similarly, when I look at the minimum value, so one thing you'll see that the minimum credit that a bad borrower takes is also is much higher than the minimum credit that the good customer takes. So that again is something that minimum, so that difference in the profiles of the customers is clearly observed through this minimum value, right? So just have a look at the minimum value over here. So there is a 73.2% difference. So the minimum balance taken by a bad customer is 73.2 times more, 73.2% more than the minimum balance that a good customer takes. So again, that difference between the good and the bad is coming out very clearly. So one thing you can see is that the profiles of the borrowers in terms of the amount variable is actually very different between the good and the bad borrowers. So this is another important observation that we have over here. Right. So similarly, if I look into the 95th percentile, it's the same thing. So there is a 53% difference, or the 50. So this is like 53.06% more than the 95th percentile value of the good borrowers. So similarly, I can extend the 3 over here. So obviously at each stage you can see. So if I look into across all the descriptive measures, I can clearly tell you that yes, this difference. So I can clearly say that yes, this difference is there. So this difference is like the difference in this descriptive measures is actually very, or it clearly shows that how different the profile of the borrower is. So if I use the amount variable into my model, right? So this descriptive analysis will show that if I do this for the amount variable very clearly will be in a position to distinguish between the good and the bad borrower. So what it means is that if I just use the amount variable in my model and I develop a model, I should see a clear distinction in the average behavior of the two variables. Right. Okay. So this is the difference in the empirical distribution of the difference in the central tendency of the empirical distribution for the amount variable. Right. This is the difference in the central tendency of the empirical distribution, and the variable over here is the amount variable. For the amount variable, you are doing this, right? Now, from this, from the differences in the measures of central tendency, we can clearly say that yes, there is a very clear difference in the profile of the borrower. Now, similarly, over here, so I have three measures over here. Okay, so I'll just do this. So this is the central tendency. This will be the dispersion. Measures of the empirical distribution or amount. This is the measures of dispersion. The measures of dispersion. Okay, so if I look into the standard deviation over here, so over here, one thing that we can clearly see is that now have a look into the measures of dispersion. So the standard deviation in this data in the for the bad accounts is higher. So what it shows is that the average behavior of the variable, the average variable, or the average of the amount variable is higher for the bad borrowers, which is perfectly intuitive. And you expect that as you move from 0 to 1, the average of the variable would reduce. But also what happens is that the lending with the variability in the figures, right, which is there for the bad borrowers, is much higher. So the variability in the figure is very high compared to the variability of the figures for the good borrowers. So what it shows is that the consistency in lending to the good borrowers have been better. But for the bad borrowers, this percentage itself has been, or the standard deviation or any other measures of dispersion has actually been very high. So over here, and that and how do you assess this, or how do you capture that consistency? That consistency is captured through the coefficient of variation. So the coefficient of variation is nothing but the standard deviation by the mean into 100. So it measures the standard deviation as a relation or as a percentage of the mean of that group, right? And from there, one thing that you can clearly see is that the lending, so whenever you are lending out to a bad borrowers, to the bad borrower, the borrowers who turn out bad, right, seem to exhibit higher volatility in the exposure pattern, in the exposure amount compared to that of the non-defaulters. So non-defaulting borrowers are more or less homogeneous, and the risky, because the riskiness of the defaulters is higher, right? So of defaulting another accounts who would default is higher. So therefore, the variability in the lending patterns associated with this borrower is also very high. So that's the part that we would see over here. So that's the part that's the picture that this distribution is showing over here, or showing in this particular graphs, or in this particular exercise. Now over here, what we need to do is, or what you need to do is, so if you want to actually plot that distribution, and you need to plot this, so we use the univariate analysis, the univariate procedure, to plot the distribution and for further in-depth analysis, right? Now, as Shiva had identified that this distribution has a mean which is higher than the median, it is slightly biased towards the upper end values, and there is ample evidence in this case that there are some extreme tail end values in this case. So therefore, one thing that we can safely conclude about this distribution from these descriptive measures is that it's a right-skewed distribution, because in this distribution the mean is greater than the median, right? So what it means is, if the mean is greater than the median, it means that there is, so the mean lies to the right hand side of the median. As a result, this is an outcome of the extreme tail end values that the mathematical distribution has, right? So over here, if you look into this distribution, let's further look into the distribution. So I have the 25th percentile. So what it says is that 25% of the population takes a loan of less than, so 25% of the population has applied for loan which is less than 1,350 Deutsch marks, versus for the good customers it is 1375. So you see that at the lower percentiles the good customer shows a higher value, but as the values increase, right, so the value the difference between the value of the bad customer and the good customers keep on increasing, because when you move on to the 50th percentile, so it covers half of the data. So it says that for the bad borrowers, right, the borrower turned out bad, we see that 50% of that population had taken loan which is less than 2,574, whereas the good customers, for the accounts which that turned out to be good, this amount was 2,244. So you can see that at each stage this difference is kind of increasing. So basically the difference is the difference between the minimum values is the highest over here, right? So as you move from the percent, as you move to the higher values of the percentiles, you will see that that the two values start becoming closer and low, like the maximum and the maximum values are relatively closer than the minimum values. So over here, one thing that we can see is that either for the bad customers, the overall variability is higher. For example, over here you found if you go to 75th percentile, so it shows that 50% of the population has loan with 25,000 2,574 less than equal to 2,574, and 75th percentile of the population shows that 51 so 75% of the population has loan between 5154. So between 50th percentile value to the 75th percentile value, the amount of credit has increased, and it is nearly double, right? So it is nearly double. So the amount of credit has doubled. So between 50th percentile and 75th percentile, the variability in the distribution of the bad customers have increased. So if you look across this 2,574 and 5,154, we will see this minus this divided by this. So it is more than 100% increase. So it is nearly doubled, right? 100.2%. So it has nearly doubled. So from the 50th percentile to the 75th percentile, your value has nearly doubled, right? So this shows that so now if I go from 25th percentile to this maximum of the 99th percentile of the maximum percentile to the next 25th or 25 percentiles, you will see that the variable has increased, the variation has increased even more. So your maximum value is this minus this divided by this. So it is 2.57. So it is now 257% more than what it was in the 75th percentile. So from 25th percentile to 75th percentile, and from 75th percentile to the 100th percentile, right? So you will see that these figures have just been doubled. So similarly between 25th to 50th. So what is the difference over there? It is like 90%. Right. So the 50th percentile figure is 90% of the 25th percentile figure. So I'm saying that this, so the moment from 25th percentile onward, the variation has kept on increasing. Whereas for, if you see for the good borrowers, it is something like 50th percent, the 25th percentile, it is 63.2%. Right. So from this particular part, what you have is, so if I compare that between the 75th percentile and the 50th percentile over here, see it is near the growth is more or less stable for the good borrowers, right? So from 75th percentile to the 100th percentile. So yeah, so the variability has increased on 75th percentile to the 100th percentile. That's fine. But between till 75th percentile, the growth has been very simple. So if I look into this at an interval of 25, right? So this shows that the variation. This also proves that the variation in the bad customers is higher, is relatively higher than that of the good customers, right? So obviously, so this shows that the amount, so obviously this shows that with the higher the amount is, higher will be the chances of the bad customer, and hence this variable will have a positive relationship with the risk, as well as if I include this variable, the profile or the descriptive measure of the variable is very different across these two groups, and hence we can also conclude from here that so we can also conclude from here that this is something that so this also shows that the variable, the variable amount is very useful for, so is useful for, so this approach of assessing the empirical distribution is very useful for variable selection. So you can clearly see that the descriptive measure of this variable across the two categories is very different. So this analysis gives you a basic insight into the into a continuous variable, right? So any questions up to this point?
Hello. Hi, sir. Actually, I have a question out
Yeah,
of the country. Sir, actually, I want to know what does the impact it has if the missing values are replaced by the mean, median, or mode, or either zero also, and what does influence it has also on outliers if it is replaced by the mean? Is it so? Usually, outliers are replaced like by the percentiles, like 95, 99. So, and I want to ask about the missing value also. What does it impact it has?
okay, okay, fair enough. So anyways, I will be taking this up at length at the later part of the discussions of this central tendency measure only, but I'll give you
Okay.
a brief idea. And I think I had discussed this previously as well. So when we were doing that SAS portions. So I'll clarify that answer once again. So when we talk about missing observation, missing imputations or outlier treatments, right? We cannot always use a mean imputation. A mean imputation can only be used for variables which are not account level information. Now, if a variable which is an account level information, like the amount variable over here, or for that matter, that check account variable, or for any account level variable or variable for which an account level information is available. Now, if I have a missing value over there, I cannot help much. I cannot do anything to just to include it with the mean. In such a case, the data has, the cause of that missing value has to be investigated, and a imputation has to be made accordingly. So for example, I have a variable like, say, month since last delinquency. So delinquency, as we know, is an outcome when, and so it is when you have missed out a payment, and only then that, so if someone has missed out a payment at some point in history, but has not missed, or has missed out at some point in the history, only then the month since last delinquency can be populated. So for populating it, you need the date, the reporting date, and the date when the account had last gone delinquent, You create a difference between the two, and from there you have the month since last delinquency. Now with this exercise, now let us consider an account which has never gone delinquent in the entire history till now. So for that account, the month since last delinquency will be a missing value. Now the question is, can I do a mean imputation in this case with all the other values of the variable? No, I can't do that. The second question is, can I impute a zero over here? I cannot do that, because if I say the month since last delinquency is zero, it means that it is this current month that the account has gone delinquent. So I cannot do a zero imputation either. So I'll have to find out some way of imputing that, right? So the best possible way to impute that is, so in order to remove that missing value, what you do is you put in a special value over there, which will demarcate those values. So let's say you put in a special value like 6 nines after that. So when you are doing any deciding exercise, those variables which have never gone delinquent will go either right at the top or right at the bottom, because these are non-delinquent customers, so they'll have the lowest risk. So it is always good to have them right at the top. So what you do is, so your month's last delinquency has values like 0, 1, 2, 3, 4 like this. So the best thing that you can do is you say that, boss, I'm going to put in some negative special figures. Let's say I put in a value like minus 9999999, 6 nines. So when you do a deciling exercise, that minus 99999 will come right at the top, and after that 0 and all will start. So you know that minus 99999 is those accounts which have not been delinquent ever, and hence month since last delinquency is not available for those. So that's where you update, you create that as a criteria in your data dictionary, or data dictionary has a specific tab which talks about special values assigned. So once you assign that special value, you create that and you keep that noted. So whenever you are calculating averages for that variable, all those records which are minus 99999 are removed, and on the other values the averages are calculated. So that's one way of sorting that the missing imputation problem. Now let's say there is another variable like a limit variable is missing for a credit card data. Now this is an data extraction problem. Or let's say for an overdraft data, the limit is missing. Now if a limit is missing, it means that that account does not have that OD facility. Now you cannot impute that limit. So again, that limit has to be either done through some specific, some special account or some special values, or what you need to do is you need to see why that limit value is missing over there, and if a re-extraction is required. You cannot do anything about it. But let's say you have a variable like some variable like current account outstanding balances. So current account with outstanding balances greater than equal to $500. This is a bureau variable, right? And it is highly likely that a bureau variable may not be present in the bureau for a given record. It's highly likely the hit rates of the bureau variables are very different. So such a variable you can do some kind of an imputation. Now I can do some kind of I look into so I do a decile, and I do some deciling exercises, and I see, okay, then how is it that this variable is behaving, and based on that, so what is the bad rate or corresponding to those missing categories. With the most closely linked bad rate category, I take that average of that group and I put it in there. So that way I can do an average imputation or imputation of missing values that way. Now coming to outliers. Now I need to first identify what my outlier is. So if there is an outlier, there are multiple considerations now. So can that outlier be considered as, shall I impute that outlier with some 95 or 99 percentile figures? Yes, if it's my modeling variable and there is outlier, I do that. If not, I need to check what we can do with those. What is the proportion of those accounts in the data? Is it actually very small or is it pretty significant? Right. So over here, I just so in that case, you just look into the 95, you do a 95th percentile, 99th percentile, and do an imputation. Now you can. The question is, can you use an average to do an imputation? Yes, you can use an average to do an imputation, but mean imputations for outliers is often a bit risky because you tend to lose out on a lot of information. So therefore, what you need to do is you need to do a, it is always suggested that you do a percentile driven imputation. So you do it at 95 percentile, 5 percentile, 96 percentile, 4 percentile, whatever, right? Or 99 percentile, 1 percentile, whatever. So that is another way of doing the thing. So first you need to ensure that, okay, what is that level up to which there is an outlier? And maybe that after that, whatever values are, there are good, let's say 10,000, 15,000 records or some 30,000 records with which you can create a own segment. It may be a very premier segment that that particular account has. So, so for credit cards, especially, for personal, for credit cards especially, you do have categories like premier by wealth, categories premier by income, and these have fantastically high value of limits, like, and each of the limits can go up to 15 lakhs or 20 lakhs. So even a distribution, if these are not representative, so let's say 5% or 10%, 5% of the population, so will you impute them? Because if you do the distribution of the limit variable, you will see that, boss, these are outliers. So they are very different from what the overall portfolio has. So just think about that Amex example that we did a few days back. So the Amex limits were very different from what Mastercard and Visa had. But would you actually like kind of do a imputation on them? You won't, right? Because that belongs separate product class. So that product can itself be a separate segment. So these are the considerations that would come in before you just do. So you just don't see the variable and do an imputation. Imputation comes, or outlier treatment comes at a much later stage after you have done segmentation. And in terms of those segments, you see whether your outliers are kind of capped and floored and whatever. You do a capping and flooring also to solve these outlier problems. You do 95%, 99% and treatment to solve these problems. So there are a lot of different approaches to solve outliers. So there is no single way to solve problems related to outlier. And mean imputation for outlier is just the most, is the most like under market, uh, down market treatment that an analyst can do. Right? Mean treatments are okay for missing values, but for outlier treatment, it either has to be a capping plotting exercise or a 95% 99 treatment, which is also a variant of the capping plotting exercise. So that's the way you can do it. Now, in some cases, you see that, okay, I have two groups, and so an outlier group which is very similar to a bad rate to some other high bad rate group. So in that case, you can club the groups together as well and create one separate group out of it. So there are different ways, and that totally depends on the data that you work with. And mostly these outlier treatment happens for so mostly this happens on the, mostly the outlier treatment happens after all segmentations are done, because at the overall level you cannot do any outlier treatment. You can identify outliers as well. So what you can at most do is you can, so to accurately identify outliers, outliers are treated with respect, because outlier, what are outliers? Outliers are nothing but something which is not representative of the group. So for that group, what you do is you first develop segments. So the moment you do your appropriate segmentation, do a effective segmentation, half of the outlier problems are solved. And whatever remains for a few couple of variables, that can be fixed using flooring capping exercises, and which is actually the more accurate measure of doing thing. Mean imputation is like mean, like doing it with mean is possible if the extent of skewness in the distribution is not very high. But if it's a fairly skewed distribution, which mostly is the case, then it's always suggested that you do a flooring capping exercise. That helps you solve the problem better, right?
Yes, sir. Thank you, sir.
Okay. Okay, perfect. Fair enough. Now the next question is, I want to understand in this distribution, now because we are talking about outliers, does this distribution have an outlier? How do I identify that? What is the most easiest way to identify this? Okay. Now, what does outliers do? Outliers are non-representative. Outliers are non-representative uh, behavior of a data. So they are the, or which is non-representative. Now the next question is that if they are non-representative, they are the ones which will be outside the purview of the normal distribution, right? It will be outside the purview of the normal distribution. So that means that the values which are outside the limits of the normal distribution are the ones which are truly the outliers, right? So that's where I need to find out. So that's one of the most simplest way for me to find out. So so it's one of the most simplest way for me to find out this to find out this outlier is to assess the limits of the normal distribution. So by the law of large numbers, we know that 99. So if a distribution is normal or if a distribution is symmetric, then 99.97% of the observations must lie within the mu plus minus 3 sigma limits. Now, if there is a value which is lying outside that limit, that truly is an outlier because it's just 0.03% of the observations lying outside. So that's truly an outlier, right? So it does not represent the 99.97% of the data set. So if I can track those values, so which are the values, which values are those, then I can clearly identify what the outliers are. So I need to find out. So if the so identify which are the points. So what I first need to do is I need to identify that which is that point which is lying within the plus minus 3 sigma limit, and out of that the values which is lying outside that limit are my outlier. So what is that value? What is that value of plus minus 3 sigma limit? That is the first question that we need to address over here, right? Then I don't even need to look into the percentage of the population, right? So that would be important if I have to look in, if I were to look into the skewness. But just to assess, okay, how much of the records are, so what is that limit outside which the values will be considered to be outliers? That's what I first need to understand. And one of the easiest way to identify that is to look into the mean plus 3 sigma limit. So any value outside the mean plus 3 sigma limit will be your upper end outliers, and any values between your mu minus 3 lower sigma limit will be your lower end outlier, out that limit, and anything outside and below that will, above or below this limit, will be treated as an outlier. Then we need to see what value, what is the nearest value in the percentile distribution corresponding to that. And then we can identify, okay, this is the value at which we will cap the distribution or floor the distribution. So that way you will always get an idea of how to work with outliers also. So through this, So through a basic descriptive analysis of a variable, these are the different insights that you can form about a variable. So let's try to check the outlier part.
One minute. I have one doubt in this.
Yes, tell me.
So here we will be using standard deviation to calculate the 99 point by using the empirical formula. How many values are inside that? But that thing we apply on the normally distributed graphs. So if we apply that concept here, it will be biased towards the right?
Yeah, so
Because
you will
it's
not
right
get
skewed
that ideal
distribution.
percentage. So that will show whether it's a right skewed or a left skewed distribution.
So how can we apply that thing here? Because it's not a normally distributed,
Yeah,
as you
so you
said.
will not get that distributions for the normal figure, right? And that deviation will show you whether it's a right skewed or left skewed. So if it's a right
Okay.
skewed distribution within plus minus 3 sigma, you will get more concentration of numbers. And for so within plus minus 3 sigma, you need to have 66.67% of the observation if the distribution is symmetric. So if it's right skewed, that means greater concentration will lie over there. So it will be more than 66.67%. So you know that the greater concentration is towards the lower end values. And then as you increase that limit, so within plus minus 2 sigma, you need to have 95% of the values. You will have something less than 95%. And outside that, within 99.97 plus minus 3 sigma, you need to have 99.997%. You will have lower percentages. And a greater percentage of numbers will lie outside that 99.97% if your distribution is a right skewed distribution. So those percentage differences will differ between plus minus 1 sigma, plus minus 2 sigma, and the deviation from the normality will give you an idea whether the distribution is a right skewed or a left skewed distribution.
Can we use here median also as a mean to observe and differentiate if we are using median as a mean and if we are using
How can you
mean
use a median as a mean? The moment you use a
because
median as a mean, right? So that the moment it becomes a normal distribution, right? So how can you use a median as a mean?
but the empirical formula usually we apply on the normal distribution in that way I said actually.
See, the
So
empirical
okay,
formula you cannot apply, or empirical distribution cannot apply to a normal distribution. That normal distribution or that z-score comes from a theoretical distribution, and the
right,
empirical distribution is obtained from the descriptive measures. So from the
right,
descriptive measures, you see how is it that the values are distributed. So if you use a plus
right.
minus 1 sigma, on the expected distribution, you will get some percentage of observations lying within that interval. Now, if it was a normal distribution, then it should have been 66.67%. Now, in the empirical distribution, you have, let's say, 71% within plus minus 1 sigma. What it means is that greater proportion of observations are concentrated in plus minus 1 sigma compared to what it would have been had it been normal. So that 66.67 is a benchmark. It is not an empirical, so it is not based on the observed distribution. It comes from the theoretical normal distribution. So what it says is that if the distribution had been normal, then there would have been 66.67% of the observations lying in the normal distribution, lying within plus minus 1 sigma. Now from the empirical
But
distribution, I
then
calculate a mean plus minus 1 sigma. Now, when I calculate that mean plus minus 1 sigma, I get a certain percentage of observations lying within this. Then what I say is that, okay, I see 71% is lying within plus minus 1 sigma. Ideally, it should have been 66.67%. So what it means is relatively greater proportion of observations are concentrated in the lower band of values. Therefore, it gives me an idea that, okay, there is a certain deviation from normality in this distribution, mostly right skewed, because a
right,
greater proportion of the observation is in the lower part of the band. Then what you do is you
right,
take the plus minus 2 sigma limit. Now theoretically, if it was a normal distribution, 95.5% of the observations would have been lying between plus minus 2 sigma, right?
Right.
Over here, you see that 93% is lying. So you know that there is, so
Okay.
you know that had the distribution been symmetric, it would have been 95.5, but it's slightly less because in this interval, plus minus 2 sigma is a mid interval, right? So you know that lower
Right. Right.
proportion of the observations are lying. So you see that okay, the deviation exists both for plus minus 1 sigma as well as plus minus 2 sigma. So that means within plus minus 3 sigma, instead of 99.97%, you see that 97% is lying within that value. So what it means is that the remaining 3% is lying outside this plus minus 3 sigma. That 3% is the tail end distribution, which is lying outside the plus minus 3 sigma. Because it is the concentration of the observation is less than 99.97, so within plus minus 3 sigma, you say that this distribution is not normally distributed. Because instead of 0.03%, 2.3% more or 2.7% more is lying outside that plus minus 3 interval. That is why there is a outlier. So had all the values been like, if mu plus minus 3 sigma had covered all the values in the distribution, you would have said, boss, this distribution is normal. Because a substantial part is lying outside that plus minus 3 sigma value, that distribution becomes a right-skewed distribution. So this is how you will always compare the, so from the empirical distribution, you will get that percentage distribution, right? That how much,
Okay.
what percent is lying actually within plus minus 1 sigma, plus minus 2 sigma, plus minus 3 sigma. Then you will compare what should actually it has been, should have been. And from there you can find out the whether distribution is like right skewed or not. So that's the way you do that comparison. I'll come to
One
doing
last
I,
question.
anyways, I'll
Last
be
question.
doing that exhaustively at a later part of this discussion. Yes, Shiva, please tell.
One last question. So, Tanmay, as you said, the 99.97, when we go to the 3 sigma thing, so 99.97% of the population will be covered. But if the distribution is right skewed, then it will include the actually which making the distribution right skewed. It will include those outliers because the mean will be shifted towards the outlier, and it will try to exclude the actual values which belongs to the sample, which will be in the left side. Is it right?
Yes,
What I
yes,
said?
yes.
So how we will treat the outlier by using this technique?
So this is something that I just explained sometimes back to Pooja, right? That you check the plus minus 3 sigma value of what is coming in. Any value which is lying outside the plus minus 3 sigma value is that tail end values, and that is the outlier. So those values, so 0.03% of the observations, we had the distribution in a normal distribution, 0.03% would be lying outside. So what lies outside that normal tail will be your outlier, because that is not representative of the whole data. So you just first need to identify what is that outlier level. Then you need to, so then when you do the plus minus sigma distribution, you'll get to see how whether it's right skewed or left skewed. I'll come to this. I'll just park this question for the time being. I'll just, when I do this in SAS, you will get to understand. Right. So just,
Okay.
yeah, I'll just come to
Okay.
that.
Okay, thank you.
Yeah. Okay. Okay. Fine. So okay. So let me just create the mean plus k sigma limit. Okay. So mean this is mean plus 1 star mean plus 2 star sigma 3 star sigma. Values. Okay, so let me just start off. So what is the mean over here? The mean is this. Plus 1 star sigma is your standard deviation. I'll make this 2 star sigma. This is a 3 star sigma. Right. So this is the values for the bad customers. So over here, what we are doing is values for the good customers. Okay. So over here, what we'll have is mean plus 1 star C. So now this is what we have. So for the good values, this is 7,473. The values over here is 5,398 and like this. So now let us try to see which is that value which goes beyond this plus minus 3 sigma. So let's have a look into the bad distribution first. Right. So the bad distribution is the plus minus 1 sigma value is between 7473. So this is anywhere between the 75th and the 90th percentile. So 7473 will lie anywhere between the 75th and the 90th percentile values, right? So let's say the 80th percentile or something of that type. Now plus minus, so within 7473 you will have nearly 70% or so you will have 66.67% of the observations if it is a normal distribution. But one thing you can clearly see here is that it lies between 75th to the 90th percentile. So it is somewhere between the 80th percentile, roughly 75 to 80th percentile will be that value where it lies, right? So it shows that within plus minus sigma, within plus minus 1 sigma, 80% of the observations for the bad accounts lie within, nearly 80% of the bad accounts lie within this plus minus 1 sigma, right? So if I just change the order of this output over here, so let's say I have T75. So let me write T. No, I cannot generate the intermittent percentiles over here using this. So the standard percentiles can be generated. For that, we need to do the univariate exercise. Okay. So over here, I can see that this. So you can see that this 7473 will lie somewhere around your between 75th to 90th. So more than 75 or more than nearly 80% of the accounts are less than me plus is lying within plus minus 1 sigma. So but had it been a normal distribution, it would have nearly been 66.67% of the observations. So one thing I can clearly say is that because it is a right-skewed distribution, majority of the observations are lying within plus minus 1 sigma. 80% of the observations lying within plus minus 1 sigma, whereas ideally it should have been 66.67% of the observations, right? So therefore, this clearly shows that this values of so this is for the bad accounts, right? So this distribution is more skewed to the right. Now for the good accounts, the plus minus, this is 5,386. So where does 5,386 lie? So again 5,386 again lies between 75th to the 90th percentile. So it clearly shows that this number, right? So nearly 80% of the records, nearly 80% of the records for both the goods and the bads lie within mean plus minus 1 sigma. Had it been a normal distribution or a symmetric distribution, 67% of the observations would have been lying in this interval. Now let's move to mean plus minus 2 sigma, that's 11,009. So 90 to 95th percentile. So 95th percentile is 11,968. So basically, let's say it is anywhere between 92 93 percentiles. So basically, I can say that nearly 92% or 93% of the observation is lying within plus minus 2 sigma. Had it been the normal distribution, it would have 95th per 95.5 percentile, 95.5th percentile figure would have been this. So I can see that within 95th percentile, with 95.5 percent, like lower percentage of the observations lie within plus minus 2 sigma. This is again, so compared to 95.5%, nearly 91 or 92 to 93% of the observation lies within plus minus 2 sigma. So the additional 2% of the observation falls under mu plus minus 3 sigma. So the mean plus minus 3 sigma is 14.545. Had it been a normal distribution, 99.9% of the observation should have been there, right? But over here the 99th percentile is 15,284. So this lies between 95 to 90, 95 to 99. So that is less than 99 though. So nearly 95 to 97th percentile of the observation is at 45.5, 14.545. So any figure between 14,545, more than 14,545, will be treated as an outlier. So basically we can see that nearly 2 to 3% of the records lie beyond mu plus minus 3 sigma. Therefore, this value is the 97th percentile figure, right? So then the capping should happen at 97th percentile. Corresponding to this figure should be the percentile figure, the exact percentile figure corresponding to which this the mapping should, or the capping should be done, because any values after the 97th point, because the 97th percentile figure of the skewed distribution represents the 99.97th percentile figure of the normal distribution. So beyond this, all the distribution is like, so it becomes drastic. So then it comes outside that interval. So therefore the capping for all records which is above 14,545 for the bad records must be taken care of, right? So similarly for the good records, you will see that the same plus minus 3 figure is 10,189. It is much lower than that of the bad borrowers. So from whichever aspect you try to look into it, you see that amount variable is perfectly a rank ordering variable. It risk orders both these two groups very nicely. It can distinguish these two groups very nicely, right? So therefore this variable will enter into the model as an important variable, right? Okay. So over here, so I'll repeat once again, had it been a normal distribution, then 99.97% of the observations must have been, 99.97% would have, percentile value would have been a value of 14,545, 45.59. But over here we see that that value is somewhere between the 95th to the 99th percentile. So it may be the 96th or the 97th percentile value. So therefore, in this case, the capping, so we can say that after 97th percentile, all the values are outlier because they are lying outside the plus minus 3 sigma zone. Therefore, we should say that the capping of the outliers must happen at 97th percentile and not at 95 or 99th percent, right? So that's how we will infer about, that's how we'll try to identify the outliers for both the categories, and at a category level try to do the so at the category level you can do the capping. But yes, ideally when you are doing the capping, you will not be doing it at in terms of the target variables, because when you are running the model and if you have to do a capping flooding, you cannot do it with the target variable because the target variable is not there. For descriptive measures, you can do it as a target variable to see whether this variable is working fine. So basically so your model segments would actually help you to do that. So that is the part. So this is how we can identify whether, we can also identify whether a distribution is right skewed, as well as we can identify the outliers and thereby fix it, right? And to do all these exercises, this empirical distribution, or assessing this empirical distribution, looking into analyzing the descriptive measures, is the most important part, right? So this is something, so this is how we generally look into the basic a distribution, or you can say that this is the level 1 analysis of the distribution. So as we call it, this is the level 1 descriptive analysis. Overview of the empirical distribution of a variable, a continuous variable. Right, and the variable is
So Tanmay, here we can get the percentage of outliers like maximum minus mean plus minus 3 sigma. That is whatever the value you're getting divided by mean plus minus 3
no,
sigma.
no, 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 no. That will be a deviation. But no, I need to find out the percentage of records. So for that, I have to do the deciding exercise. So we'll come to that.
Any
Here
value.
we have not
Okay.
get dug deeper to so deep, right? So, but first, what we need to understand is that, so if I have to do a hot, quick, and a dirty analysis of a variable to get some insights into its behavior, so this is what we should do. This is how we should get it for the mean value and all. I mean for the given variable. So any continuous variable should be treated in this manner. Right? So this is the level 1 descriptive analysis that you would need to write. Okay, so after this, the next thing that becomes, the next thing that ideally would happen is we would want to understand how to dig deeper now to understand how is this variable behaving. So is this variable behaves in sync with what the intuition is. So that's the next part of the discussion that we have. Right, so that's the part where we talk about the deciding exercise. We'll talk about the ranks and plots. So but let's stop here for the day. Right, I'm uploading this recording and go through the code sheet, go through this code, go through this explanation, try to understand what we have done and how it has been done, and then we will regroup again. So we'll regroup this week, right? Last week I thought of regrouping, and I've been thinking this for quite some time to do two, 3 sessions on the weekday evenings, uh, so that I can cover up the backlogs. But because of my health issue, I have not been able to do it because of the vaccine thing and all. So let's do something. Let's regroup over the week for one session, at least 1 or 2 sessions this week. I'll tell you the time one day ahead, and we will do we'll talk more about the descriptive analysis, the level 2 and the level 3 analyses, and how to keep on going and do a full-blown descriptive analysis for a variable using proc means and univariate, when to use what, and the how to do the deciling exercise. So in deciling, let me tell you, in deciling what you are doing is you are dividing the variable of 10 groups. For percentile, what you are doing is you are dividing it into 100 groups. For assessing the variables and doing the ranks and plots analysis, assessing the actual versus expected relationship of the variables, deciling is preferred because you divide it into 10 groups rather than dividing it into 100 groups. So that is one of the measures that we have. So let's try to so we'll discuss more on this. Let's try to regroup over the week. I'll tell you the date. Till then, go through this video recording. This video I'll be uploading it in the next 3 hours, and then go through this as well as the Excel sheets I'll upload so that you can go through them and take a couple of days, go through the nitty gritties, try to understand what I've explained today, and then we'll carry on from there, because this is a very critical part. Remember, right? Because without this analysis being correct, you'd feed in garbage to your model, the output that you will get will be a garbage. So we need to prevent that part. So we need to understand it very deeply, in great depth, how these statistical measures are being used for development and various other exercises. Right? Okay, so thank you guys. Thank you for your time, and let's catch up sometimes over the week. I'll tell you in the time ahead of you. Right? So thank you guys. Thanks a lot. Have a great weekend.
Thanks. Yeah, thank you.